plus some time for discussion afterwards. Thank you.
As Jean-Luc mentioned this morning, Planck has greater capability than previous CME experiments, and therefore we have to demonstrate lower systematics. We have lower noise, we have to have lower systematics. How do we demonstrate the correctness of the results? There are several things that will be threads throughout the week. You've already heard this morning. We show that methods work in realistic simulations, and we show internal consistency. Planck has redundancy in many ways, each of which provides its own tests. We have multiple detectors at a given frequency, and we can compare the output from one detector to that of another. You've seen examples of this already this morning. Planck spins at 1 revolution per minute with its axis fixed for 39 to 65 rotations. That set is called a ring, and we can compare data from the first and second halves of a ring. It's a technique you've already heard about this morning, but it's a critically important technique, half-ring differences. In the half-ring differences, the sky signal subtracts out, leaving noise and possibly other systematic residuals. It's a very powerful test. It's a feature of the scan strategy that we would not want to be without. Half-ring differences can be constructed for single or multiple detectors and for any period of time longer than a couple of minutes. 2 spins being the minimum, or 1 spin being the minimum, you can take, or 2 spins, you could take half of that period and you have the same sky. In addition to that, we have multiple frequencies. Foregrounds change, but in appropriate units, the CMB doesn't. You've already seen examples of the use of multiple frequencies in cross-checks. Then we have multiple coverages of the sky. In 6 months, loosely called one survey for convenience, Planck covers most of the sky once. It's about 85% in 6 months. It's because we steer the spin axis on a cycloid 7.5 degrees so that all of the feeds cover the pole eventually. In survey difference maps, the sky signal subtracts out, but the effects of different beam orientations and side lobes leave residuals, so we have a test there. In 12 months, Planck covers the sky twice exactly. Marco will talk about this on Friday and show how these coverages line up. I have a dead laser. Can anyone supply a laser? All right. Good. You've seen examples this morning of all of these tests, and in fact, you saw one example of this. What I'm going to concentrate on today is yet another level of redundancy that Planck has that is important in demonstrating correctness and consistency. And that is that LFI and HFI, 2 different instruments, 2 different technologies, different systematics, in fact, different teams, different processing. Almost everything is different between LFI and HFI. And that provides a powerful test of consistency. Let's start at the map level. Now, we're going to do this before component separation. And to make the best comparison then, that's because it's the most general possible way to do this, before a lot of other processing. The foreground minimum is at 70 gigahertz, as you have seen. And to make this comparison then, we'll compare 70 gigahertz with 100 gigahertz, the 2 frequencies closest to the foreground minimum. Once again, different technologies, different systematics. Here are the 2 maps. 70 gigahertz is usually shown at inside 1024, but here it's made at 2048 to be the same as the 100 gigahertz map. Here's the difference between them. The red here in the galactic plane is mostly carbon monoxide. The blue is mostly free. But the CMB is gone. It may be a little hard to tell that the CMB is gone. Let's take a blow-up of a small region in the clean part of the northern sky near the north ecliptic pole. Here's 70 gigahertz. here's 100 gigahertz, and here's the difference. And now you can tell very cleanly that the scale of the stuff that's left here is not the scale of the CMB. It's noise. And in fact, it's noise dominated by 70 gigahertz because the 70 gigahertz is plotted at NSide 2048. In fact, the resolution of 70 gigahertz would not lead you to make a map at that scale. Visually then, this is spectacular agreement on the signal in the sky. Quantitatively, though, you don't get numbers from the visual impression. So we'll look now at the power spectrum level. In making a comparison, you have to be extremely careful not to introduce artifacts just in the comparison. Extreme care has been taken. Identical masks for 70 and 100 gigahertz. The union of all the foreground masks used in the diffuse component separation that Mark and Carlo showed, plus all of the sources in the PCCS are masked out. You have to get the appropriate beam and pixel window function corrections. And you have to be careful about monopole and dipole removal. All of that's been done. Here are 70 gigahertz in red and 100 gigahertz in blue, plotted on top of each other. These are beam and pixel window corrected pseudospectra, minimum processing. Mask kernel inverted to 4 pi amplitude debeamed, technical terms. Now, what you see here is, well, you can't tell any difference on this plot all the way up here to the first peak. Then at this point, you see a bit of a difference down here at around 350. You see a difference, and then as the noise picks up, you start to see some differences. Here's noise, 70 gigahertz. Here's noise at 100 gigahertz. To compare precisely, you have to be careful also to avoid noise biases. So we want a metric that uses only cross spectra. We go to the next slide, and I should point out that the binning here is 20 in L, and the fraction of the sky that's used is 63.2% in surviving mask. This is a complicated plot. We have the same L range, 50 to 650, as in the previous plot. What's on the vertical axis is relative difference, 70 minus 100, in things that I'll go through in a second, with respect to 100 gigahertz. So it's scaled to 100 gigahertz. And the numbers here, 0, 0.01, 0.02. This is 1% then of 100 gigahertz. It's the same fraction of sky, 63.2%. It's the more details of the mask, the same L binning. Okay, now the curves on this map are color-coded. There are 6 of them. The cyan one comes right along here and then starts to move a little bit. That is, and the notation here is frequency is the number, 70 and 100. And it refers to the map, 70 gigahertz map, and the half ring first half and the half ring second half at 70 gigahertz, the half ring first half ring second half of 100 gigahertz. So it means every ring, you take the first half, you take the second half. Make the maps separately. And this is to get so that you only have cross spectra, no noise bias. Then there are 2 curves here that we'll come to these one by one. 2 blue curves that you see wiggling along here, red and pink wiggling along here, and green. So let's talk about the cyan one first. This is 70 half ring first half minus 70 second half, crossed with 100 first half minus second half. And the factors of 2 are in there to make sure that the noise power propagates appropriately. You're taking half rings, so you have twice the variance, so forth and so on. And that's the curve that's down here right along 0. It flares up as expected for just noise, noise cross correlations between frequency 0. It's beautiful. It's what you want to see. So that's where we start. The second curve, let's take a look at this one, the green one. This is 70 half ring 1 crossed with 70 half ring 2 minus 100 half ring 1 times crossed with 100 half ring 2. This is the cross spectrum equivalent of this difference on the previous slide, taking the ratio of those two curves. This would be 70 cross 70 minus 100 cross 100, all divided by 100. That's the scaling on the axis. So it would be 70 over 100 minus 1, and that's the 0.01, 0.02, etc. So this is the cross-spectrum version of that. But in dealing with power spectra and manipulating power spectra, there's some things that aren't necessarily rigorous about that. So there are a couple of other metrics here that take care of to make sure that noise propagates, so forth and so on. So let's look at this one, the blue one. We have 70 half ring 1 minus 100 half ring 1, 70 half ring 2 minus 100 half ring 2, and the opposite combination, 71 minus 102 and 72 minus 101. This is a cross-spectrum estimator of power mismatch. Now, what could produce a power mismatch? Well, if there's some difference in the CMB sky, there would be a mismatch. If there's a difference in side lobes, if there's a difference in foregrounds, if there's some systematic, anything like that will be included in here. And this is before component separation. So we've got all of foregrounds at 70 and 100 gigahertz. We're masking out the galactic plane, of course, and all the sources and so forth, but it's all there. Okay, so this is an estimator where noise propagates appropriately. You could say, well, what happens if there's a multiplicative gain factor that is wrong somewhere in the process? That would scale quadratically or propagate quadratically in this estimator. So you'd say, well, a gain would be suppressed. So here's another estimator. And the first half of this estimator is replaced by the sum. 70 half ring 1, 100 half ring 1, added together. 70 half ring 2, 100 half ring 1, half ring 2. And the second part is exactly the same. So in this one, a gain difference would scale linearly. Now, what do you take away from all of this? Any estimator that you'd like, and it takes a little time to think about what's actually represented here, but any estimator that you like gives you a small difference between HFI at 70 gigahertz and LFI at 100 gigahertz. And this is rolling in everything. This is foregrounds, this is systematics, this is side lobes, this is whatever. It's rolling it all in. If you smooth the green curve, which doesn't have such good strictly mathematical properties as these, but if you did that, you'd still get something that on average is 0.5%, 0.6%, something like that. The difference between the green and the pink is really a factor of 4 on these pink, or on these spiky things, and that's just built into these factors of 2 that take care of the way the variances go with half rings, so it's more strictly correct in terms of propagating noise. But another thing to point out, suppose that there was an error. Suppose that the CMB was different between these, that there's a multiple of one or the other. You would see something here at the first peak, centered on 2, you would see a big bump. You don't see that. It doesn't flow through. There isn't anything that says there's a CMB error. So you look at this, and just the takeaway conclusion from this is that HFI and LFI are agreeing to a fraction of a percent or better across across this range. That is really good. Okay, a couple more tests. This is also ways of comparing HFI and LFI. Residual dipoles in the calibrated maps test the quality of calibration with respect to the dipole as measured. We use the WMAP dipole as the dipole that we calibrate to in 2013. It will be the orbital dipole, or orbit modulation of the dipole in 2014, but we use that for this year. And if you look at residual dipoles, these are less than 0.1% for HFI and less than 0.3% for LFI. Recalibration factors maximizing CMB consistency have been calculated both for simulations and for two multiple ranges in the data, 50 to 300, 300 to 700. You probably can't see the difference between the black simulation points and the blue 300 to 700 points. But just look here in the middle. They're all referenced to 143, so they're right there at 1. But this is 1.005, so 0.5%. And what you see is 100, 217, and 70 all have these recalibration factors less than 0.3%. That's real good too. Now another way to look at some consistency, this is multiples from 2 to 60 after component separation. And it shows Commander, Nilk, Sevim, Smika that Mark talked about, and the separation and the CMB map resulting from that. And it shows WMAP 9. And it's pretty hard to see the separation between the 4 component separation methods in Planck. But you can see a difference of about 2.5% with WMAP. WMAP is consistently 2.5% higher on average. You can see it better here. The yellow is sticking up above the line. This is the Planck best fit model. And down here in the difference, this is 1 sigma uncertainty due to noise that's shown. So that, as far as the Planck 4-component separation methods leading to maps, that is, once again, spectacular agreement and an interesting difference with WMAP. Here's a figure from a different paper. I didn't point it out, but I have listed in the corner here which papers these figures are from. This is the 100 cross 100 gigahertz spectrum from Planck in the pink purple points, and its WMAP V and W spectrum multiplied by a factor of 0.976, same 2.5% as you saw before. Down here you see residuals with respect to the model. Remember, this already has WMAP adjusted by 2.5%. And you see with that change, quite good agreement. A shift systematically in the WMAP residuals towards the high end. But you see over this intermediate range, we see that comparison. Taking all of this together, it just emphasized, pay attention the rest of the week. The Planck hardware and scanning strategy afford a wide array of consistency tests. You've seen some already, you'll see more, over and over. Planck's performance on these tests gives us confidence that its unprecedented sensitivity is being realized and that its scientific results are robust. There are a number of corrections and improved calibration and analysis procedures already identified that will be implemented next year. And everything we know suggests that these will only improve this level of consistency of the data and bring HFI and LFI into even closer agreement. It's already really, really, really good. Thank you.
Well, thank you. Questions, Reno?
Can Charles, you said correctly that Planck is made out of two very different instruments, different technologies, different here and there, I mean, totally different, but with a single telescope.
Yes.
And that's important.
Yes, it is. And in fact, going back to the comparison of LFI and HFI, it's the same telescope, but it's different locations in the focal plane, different side lobes, so forth and so on. All of that is rolled into that comparison already. So, looks very solid.
Any more questions? Yeah, one.
What's the difference between the WMAP and Planck Duto?
Don't know. Subject of intense investigation around the world.
Okay, thank you. The next speaker is Mathieu Tristram from the Linear Accelerator